Fantastic. So it's 12:15, but we are going to wait 2-3 more minutes for the students who are in the class to who are just dismissed from the class to join our meeting. After 2-3 minutes, we can start. Umut, would you like to start sharing your screen so we be sure that everything is okay?
Yes, definitely. Is it visible now?
Yes, perfect.
Okay.
Okay, great. Maybe let's start. First, thank you everyone for attending our first machine learning launch seminar series. Today it's my pleasure to welcome Dr. Umut Shimshekli, who is old friend and also collaborator of mine. Umut is a tenured research faculty at INRIA in Paris. and he received his PhD degree in 2015 from Bogazici University in Istanbul. During 2016 to 2020, Umut was affiliated with the Signals, Statistics, and Machine Learning group at Telecom Paris as an associate professor, and he visited the University of Oxford Department of Statistics during 2019 and 2020 academic year. He's a laureate of the European Research Council starting grant 2021, and his current research interests are in the theory of deep learning. We can't wait to hear this brilliant talk by Umut. Umut, the stage is yours.
Thank you very much, Sohail, and thanks a lot for the invitation again. It's a pleasure for me to be the first speaker of this nice seminar series. So today I'm going to talk about some recent findings that we found about like stochastic gradient descent applied to deep neural networks. And before starting, if there's any questions during the talk, please just interrupt me or send a message that so that Sohail can like ask me the question. All right, so let's start. So the talk is going to be like it will consist of 3 parts, and most likely I will only be able to cover like the first 2 parts, and if time permits, I'm going to cover the last part. So essentially, like just with a couple of sentences, just to summarize the whole talk, what we are going to do is first, we are going to empirically observe some heavy-tailed behavior in stochastic gradient descent when applied to deep learning. And then we are going to model this heavy-tailed behavior by using some stochastic processes. And then by using these heavy-tailed processes as a proxy for stochastic gradient descent, we will try to understand how SGD, stochastic gradient descent, works for deep learning. So we will try to understand the process instead of the actual algorithm, and then we will try to draw some conclusions to understand why some mysterious behavior about SGD is happening in deep learning. And in the second part, we are going to make these observations more rigorous about generalization error. And then if time permits, I'm going to talk about why these heavy-tailed behaviors like being observed in stochastic optimization. So what are the originating causes? So let's start with the first part. So I cannot get rid of this. Can you please? Okay, I cannot do this. Anyways, so let's start. Many problems in deep learning can be expressed by this optimization problem. So here, W denotes network weight. So if you think about the neural network, all the parameters of the neural network is a huge vector. W denotes these parameters. So D denotes the number of parameters in the neural network. And our goal is to minimize a non-convex cost function F, which is essentially an average of individual cost functions induced by data points. And here I denotes the individual, the loss functions that are induced by individual data points. Even though this is a very complicated problem because of its non-convex structure, in practice, like rather simple algorithms have been used to attack this kind of problems. So they are simple in terms of algorithmic sense. So for instance, stochastic gradient descent is one of the most famous algorithms to be applied for this kind of problems. And just to set the notation, SGD works as follows. We start from some initial parameter W0, and then to obtain the next parameter, WK+1, we use the previous value of the parameter minus the step size eta times the stochastic gradient. So this is a very simple update rule. And the stochastic gradient is essentially defined as a noisy version of the gradient of the original cost function f, such that instead of evaluating the gradient of this function on every data point at every iteration, at a given iteration, we choose a random subsample from the data points, which is denoted by omega k here. And then we average the gradients that are computed on this random subsample. So here, this small b is typically much smaller than this n, which is the total number of data points. So since this is a non-convex problem, SGD can only guarantee us to converge near a local minimum. So we are not guaranteed to find the global minimum. And then the question becomes, which one of these local minima is better than the other ones? And there has been some very interesting observations about SGD. For instance, let's say we have a neural network, and then we train our neural network by using SGD. and then we choose a step size and a batch size. And then we train the algorithm, and then we finally observe that the training loss is very close to 0. And we repeat the same procedure, but this time using different step sizes and batch sizes. And even though we find a solution which again gives us a zero training loss, when we compare these two different networks learned by these different hyperparameters, they give us different numbers in terms of their test errors. So when we evaluate these networks on some unseen test data. So this essentially means that by changing the algorithm hyperparameters, the algorithm is still able to find like a good solution in terms of the training loss, but the solutions that it provides are different in terms of the test error, so that they are not the same solution. So the algorithm is essentially finding different local minima as we change its hyperparameters. And we want to understand what is happening, and then what would be the difference between these different local minima. So can we identify and can we try to understand what makes them better in terms of the test loss, etc. So these are some unsolved questions even so far, and then this would be these questions will be the main questions that we will be interested in this talk. So in this context of like which minimum is better than the other minimum, there has been a lot of speculations, if not mathematical theories. So one of these speculations is called the wide minima phenomenon. So it essentially says that if the minimum is if you have multiple minima, if one of them is wider than the other ones, then it should be better in terms of the performance on the test set. So essentially, it means that if we have, like, this is a very caricaturistic picture, obviously the neural network landscape doesn't look anything like this, but just to explain the ideas, if you have two local minima, which look like this, even though this local minimum is better in terms of the training loss, so like this line represents the training loss, this phenomenon, this speculation essentially says that this other local minimum should be better and should be preferable, because even though its training loss is going to be higher, just because it is wider, and then it's going to be more robust in the distribution shifts. So if I shift my distribution just a little bit, this local minimum is going to be affected much more than this local minimum, just because this basin is wider in quotes than the other ones, And in this context, there has been some interesting empirical findings, which were tried to be supported by theoretical findings as well. So the first one is this paper by Keskar et al., where the authors showed that if you train a neural network with gradient descent, where there is no stochasticity in the in the optimization algorithm, so where you compute the gradient, the full gradient at every iteration, the algorithm might overfit. So the performance on the test set might not be very good. And then if you use stochasticity, meaning that if you use like smaller mini-batch sizes, where now you use the stochastic gradient instead of the full gradient, the performance of the algorithm on the test set gets better and better. And then this is quite interesting, and this means that while gradient descent is giving us some local minimum, by introducing some stochasticity, we are able to find a better local minimum in terms of this test error. And another paper published in the same year essentially claimed that stochastic gradient descent algorithm automatically finds minima like these ones, and then this is the reason why this stochasticity is improving the test loss. And then they had some theoretical arguments why SGD should be driven towards minima like this one. And we are going, like in the first part of the talk, we are going to handle the same question, but with different tools. Okay, so as I said, the main question that we are going to ask in this first part is that why would SGD prefer wide minima if it would prefer wide minima? So let's just assume that the picture that I showed you. So okay, I'm just going back. So let's just assume like this is our landscape. And then if SGD should prefer wide minima, then what would be the originating cause of this? And can we mathematically formalize this phenomenon? So first of all, since gradient descent is overfitting and stochastic gradient descent is not overfitting, then the only difference between these two algorithms is just the stochastic gradient. It's just the noise in the stochastic gradient. So what do I mean by the noise? Sorry about that. So let's define the gradient noise as follows. So I'm defining UK as the difference between the stochastic gradient computed at iteration k and the full gradient of the function f. So this is a random quantity because I'm choosing a random subset of the data set at iteration k. And then if we look at the definitions of all these like gradient f tilde and gradient f, it turns out this gradient noise is essentially an average of zero mean IID random vectors. Okay, so if we just put some unbiased estimation, unbiasedness assumption on this stochastic gradient noise, then this is essentially just an average of zero mean IID random vectors. And now, like, the question becomes, how, okay, since this is the only difference, then we need to understand like what this gradient noise is really bringing us and what does it change in terms of stochastic optimization. So the first rule of statistics, if you want to make inference, we need to make some assumptions. And if I look at this nice difference, which is an average of zero mean IID random variables, and if I want to make certain assumptions on this gradient noise to be able to make some inference, the first thing that I would do, so I found this on Twitter, is to assume some Gaussianity. So if there is an unknown distribution, I think this is the first reflex. So we just say, okay, let's see what happens if we assume it's Gaussian. So let's do that. So this has been done in many different studies. So if we assume that this gradient noise has finite second order moment, we can say that, okay, so this is just like an average of zero mean IID random vectors, and we can try to invoke the central limit theorem, which essentially says that we can try to approximate this gradient noise by using a Gaussian vector. So here I'm choosing a very simple assumption where the covariance structure is just sigma squared times identity, but we can also choose a full covariance matrix, which wouldn't change the arguments that I'm going to mention right now. All right, so now let's assume that this Gaussian assumption holds, and let's try to rewrite the stochastic gradient descent recursion. So now, by assuming the noise is just this Gaussian, I can now express the SGD recursion as a, okay, so now the WK plus 1 is obtained by WK, the previous value, minus the step size times the full gradient. So there is no randomness in this one now, plus the noise, and then here now I'm assuming the noise is a standard, noise has this specific form. And now if I look at this equation a little bit like carefully, I can see that this looks like, I mean, if you are coming from a stochastic differential equation background, you can see that you can try to mimic, you can try to model this discrete time recursion as a discretization of this continuous time process. So this is a stochastic differential equation, and its solutions are stochastic processes. Solutions are Markov processes. And if I discrete, so this is since this is a continuous time process, if I consider its discretized version, where I use a simple Euler discretization with step size eta, I exactly obtain this discrete time recursion. Then, okay, the argument is like, this argument has been done in statistical physics, like very popularly. So instead of looking at this more complicated discrete time recursion, I can try to look at this, I can try to understand and analyze this continuous time process. And then if this approximation that I'm using, if this continuous time process is a good proxy for the original SGD, the conclusions that I would draw from this continuous time process would be applicable to the discrete time process as well. And okay, so if you ever worked on Markov chain Monte Carlo, this is the very well-known Langevin equation. And here, so I forgot to mention, BT represents the Brownian motion, standard Brownian motion. And the whole reason why we have a Brownian motion here is because of this Gaussian assumptions. In the limit, these Gaussian random variables are, I mean, they are represented as a Brownian motion. And the nice thing about this is, since this is a well-known stochastic differential equation, there's a huge literature about it, and then we can try to use the mathematical tools about this equation, and then try to draw conclusions about SGD. And by using this argumentation, the paper that I mentioned in the previous slides essentially uses this model, this continuous time model for SGD. And then their conclusion is that if SGD is well represented by using this SDE, it is going to find automatically wider minima, and the width of the minima that it is going to find is determined by the ratio of the step size to the batch size. So this is the conclusion that they found. So even though this is a very interesting approach, and it was one of the first studies to tackle this problem, there have been some issues with this Gaussianity assumption. Sorry, 1 second. So the first of all, these theoretical results are often based on the invariant distribution of this Markov process. So as I said, the solution to these SDs are Markov processes, and under mild conditions on this loss function f, it admits an invariant distribution. And all these results, I mean, most of these results are based on the invariant distribution of this Markov process. But it has been also shown that when we use this discrete time recursion, the discretization, the number of iterations that we need to take for our discretization to get somewhere near the invariant distribution of the continuous time process, to be able to do that, we need exponentially many iterations in the dimension d. And given that the dimension might be in millions or billions in deep learning, so this is quite unrealistic, because like no one takes e to the 1 million iterations in their stochastic gradient descent algorithm. And the second issue is that there is a conflict with the metastability results with these Brownian-driven SDs. So what does this metastability result say to us? So essentially for this Brownian-driven SDE I'm talking about, okay, so let's summarize it as follows. So let's think that, okay, we initialize our system from this basin, and we are interested in the first time that this process exits this basin. And for these processes, it's been shown that the time required to escape this basin is exponentially proportional to the height of this minimum, and only polynomially related to the width of this minimum. So this means that if this minimum is slightly larger, slightly deeper, then there is pretty much like no chance that the process is going to escape from this region. So the probability gets exponentially small as this basin gets deeper and deeper. And then this is essentially conflicting with the idea that SGD is going to prefer minima like this ones. I mean, this result essentially says that if this minimum is like deep enough, then most likely the process is not going to be able to escape from it, no matter what its width and or the other width is. And this is more like a pictorial, I mean, this is more like a qualitative explanation, or like source of motivation, at least for me. And here I'm plotting some quantities that I computed from a real neural network. So the first, okay, let's look at the first plot over here. Here, what I'm plotting is as follows. So I'm training a neural network for thousands of iterations. So it comes near a local minimum. And then I stop the iteration. And at that given iteration, I compute a lot of different stochastic gradients. So I can compute different stochastic gradients because I can draw a different mini batch at that given iteration. And I can compute different stochastic gradients based on these different mini batches. And then for each stochastic gradient, I compute the stochastic gradient noise by subtracting the original full gradient that is computed over the whole data set. So for each stochastic gradient, I compute stochastic gradient noise, which is a vector of the size d. And then I compute the norms of each of these stochastic gradient noises, and I plot the histogram of these one-dimensional norms. So these are the histogram of the norms of the stochastic gradient noises at a given iteration. And we can definitely see that it has some heavy tail behavior, which means like we have like most of the numbers are close to zero, but some of the numbers can be really, really large. And if we do the same experiment with Gaussian data, if we just generate some Gaussian random vectors in the same dimension, and if you plot the same, if you compute the same things and plot the same histogram, the plot essentially looks like this, which is basically like a chi-square distribution. And qualitatively, it is clear that this is not a really good representative of this stochastic gradient noise. So because of this heavy-tailed structure, this Gaussian approximation is not really like rich enough to capture the statistical structure of this true gradient noise. And here we are going to propose a different thing. And so this, so I'm just leaving it as for teaser for right now, but then we are going to see that at least qualitatively, the pictures look more similar. All right, so now the question becomes, can we come up with a better model for stochastic gradient descent in continuous time such that the new model will match the original recursion a bit better than the existing modeling strategy? All right, so let's now go back to the step where we assume this Gaussianity. So we said that, okay, now the stochastic gradient noise is just an average, and we can use the central limit theorem. But then if we just relax the finiteness of the second moment of these iterates, of these elements in the summation, then we cannot directly apply the central limit theorem, the usual central limit theorem. But unfortunately, there's a generalized central limit theorem, which says that depending on the tail decay of these random variables, the average converges to a heavy-tailed alpha-stable random variable. So we still have a central limit theorem, but this time we have a different limit if we don't assume this finite second-order moment assumption. So what is this heavy-tailed alpha-stable random alpha-stable distribution? So we can think about alpha-stable distribution as like a heavy-tailed generalization of the Gaussian distribution. It's a parametric distribution with parameter alpha, which takes values in between 0 and 2. So when alpha is equal to 2, the distribution becomes Gaussian. So as I'm showing here, so this is the PDF of the distribution. So this yellow curve is just a Gaussian, it's a quadratic in the log scale. And then as we decrease alpha, as alpha gets smaller than 2, the distribution automatically immediately becomes heavy-tailed. And as we decrease alpha more, then the distribution becomes even heavier-tailed. And an interesting property is that as soon as alpha is smaller than 2, the distribution doesn't admit a finite second-order moment. So the variance is going to be infinite as soon as alpha is not equal to 2. All right, so now instead of this Gaussian assumption, let's assume this alpha stable assumption, which also contains the Gaussian assumption in the special case, but then it is more flexible and it is still obtained as a limiting distribution, the generalized central limit theorem. And then now let's try to see what kind of continuous time process do we obtain and for as a model for SGD. So by using this assumption, if I repeat all the steps that I did in order to obtain the Brownian driven SDE, I still, in this case, I still obtain a stochastic differential equation, but this time with a big difference that instead of the Brownian motion, I obtain a Levy motion, or it's called a stable process in mathematical literature, and as the difference. So similar to the alpha stable distribution, which generalizes the Gaussian distribution, the alpha stable process, this Levy motion, generalizes the Brownian motion. So when alpha is equal to 2, such that the increments of this process is Gaussian, we obtain just the Brownian motion, which is depicted as yellow here. But if we decrease alpha from 2, and the process, the increments become heavy-tailed, and the process, interestingly, might have discontinuities. This is a big difference compared to the Brownian motion, because the Brownian motion is almost surely continuous. But then whenever we use alpha strictly smaller than 2, then the process only becomes continuous in probability, which means it might contain a countable number of discontinuities, which are also called jumps. So here, like for instance, when alpha equals to 1.5, we can see like different jumps over here. And this makes a big difference in terms of the statistical properties of the process. And this is, in fact, this has a name in the literature. This is the Langevin equation driven by a stable process or driven by a Levy motion. And luckily, there is already metastability results associated with these processes. So a result from mathematical physics essentially says that. So I'm just, this is a cartoonish version of it. So it's written rigorously in the paper if you are interested. It essentially says that if we again consider the first exit time problem that we considered before, for these processes, the time required to escape from this basin is now independent from this height. So it doesn't depend on this height, and it polynomially depends on these widths and the tail index alpha. This is quite surprising, in my opinion, because I mean the independence of this height, and the reason why this time doesn't depend on this height anymore is because of these jumps. So since the Brownian motion is almost surely continuous, for the process to escape from this basin, it needs to climb up all this part because of this continuity. But since this process might have discontinuities, it might directly jump from one basin to another, and this is sometimes called teleportation in the literature. And because of these jumps, now we have a very different metastability behavior, and the most interesting part is that if this is a good model for SGD, if this heavy-tailed driven Langevin equation is a good model for SGD, existing metastability results already indicate that the process is going to prefer wider minima because of these heavy-tailed jumps. And now the question becomes, is this a good model or not? So because if it's a good model, we can just use existing theory to explain an observed phenomenon. And to validate this hypothesis, we have conducted several experiments in the paper. And okay, before going to the experiments, the picture that I didn't show in the previous slide was an histogram computed on the alpha stable random vectors. And here, at least qualitatively, we can see that the structure or the shape of this histogram closely matches the original stochastic gradient noise histogram. And okay, now let's try to make a more rigorous experiments to validate this assumption. So we have conducted several experiments where we use different data sets, different network architectures, different loss functions, different network sizes, where we increased the width of each layer, or we increase the number of layers, and we use different mini-batch sizes. So all these experiments are in the paper. And here I'm just going to show you one result because I don't have much time for the other part. And the result is as follows. So here, what I'm showing, so I have two plots, but they are showing the same thing from different angles. So let's now focus on the first one. So here, each point represents the tail index computed at the end of the training for a network with given number of layers and the width for each layer. So for instance, this point is the blue point, but so my cursor is not moving. So this blue point is essentially a neural network with two layers, and then its width, like the width of each layer, the number of neurons at each layer is around, I think 128 or something. No, it's more like 32, I don't know. So like this number, whatever this is. And then we are training this network. And at the end of the training, we estimate the tail index of the stochastic gradient noise by using some statistical estimators for the tail index. And then we repeat this procedure for different network sizes. So we increase the number of layers, and we increase the number of neurons at each layer, and then we train a new neural network from scratch, and then we estimate the tail index towards the end of the training. And here we can see that all these numbers, all these estimations are very small, like much smaller than 2. And we can definitely see that for this MNIST data set, we can clearly see some structure, some dependence between the estimated tail index and the network size. And the second plot is essentially the same thing, but this time instead of plotting the width on the x-axis, we have the depth, and then each line represents a different number of neurons per each layer, so they have the same content. So this is quite interesting, and the main interesting part is that the estimated tail indices are now like way smaller than 2, which indicates that the gradient noise exhibits a non-Gaussian heavy-tailed behavior. Because if it was equal to 2, it was close to 2, then we could say that, okay, it can be well approximated by a Gaussian. Here we replicate the exact same experiment, but this time we use a different data set. And the results are quite interesting and maybe somewhat confusing. So here we see that all the estimated tail indices are around 1.15. And we don't really see a big change with respect to the number of layers or each number of neurons per layer. But the main interesting thing for me is that still the estimated tail index is way smaller than 2, indicating an alpha stable process is a better, is an arguably better model for mimicking the structure of SGD. Right now, we cannot answer like why these changes are happening for different data sets, different model sizes. But what our main interest is that these numbers are smaller than 2. All right, so this concludes the first part. If there is any question, I can take questions. Right, so
actually, I
yeah,
I have one, Umut. So a quick question here. Like the effect of batch size is kind of I'm missing the effect of batch size in the discussion. I think the discussion is super exciting and interesting, but where is the effect of batch size?
So right now in this picture there is no batch size, but in the paper there is an experiment with respect to the batch size as well.
But from the theory side, that SDE, like what is the effect of batch size on the SDE, at least to give us
so, I mean, when we were writing this paper, we didn't have much idea, but after working on this for 2 more years, we realized that if you use a smaller batch size or a larger step size, it results in heavier tails. So it changes alpha. So if you use a smaller batch size, then you will have a smaller alpha as well. Or if you use a larger eta, then you will have a smaller alpha. And then we proved this. I mean, this is the third part. If I have time, I will go over it in more detail. But as I said, this is just a model for the discrete time recursion. But we can rigorously prove that for a specific problem, heavy tails might emerge in a different way. And these heavy tails can be quantified in terms of the batch size and step size. And the relationship is what I just mentioned right now.
Got it. So there is a question in the chat. Any empirical results on the generalizability on the test set after using this new assumption of distribution? Not sure
it's gonna be the second part, the topic of the second part. But yes, I mean, it's the most relevant question right now. So how much time do I have? By the way, I cannot see my clock for some reason.
It's 12:52, like 15 minutes should be okay, I think.
Okay, so let's directly go to the second part then. So probably we will like skip the third part, but I can take questions about it.
Okay, Umut, alternatively, you can take 20 minutes and like we can have these questions as part of the discussion. So yeah.
Okay. Let's see how it evolves naturally. Okay, so let me just close this. Yes. So I had a couple of slides about like what happens in the discrete time, because now in practice we are using a discrete time process. So here we are using like as a model the continuous time process. This time I'm using like a more general version where there are both Brownian motion and alpha stable process. And the first question that we were interested was what happens if we discretize it, and does the discretized process also escape from these like narrow basins with the same properties? And I'm going to skip the details over here. And the answer is if your step size is small enough. So here we have like a condition on the step size. If your step size is small enough, then the escape probabilities are essentially the same. So, okay, try not to read what the slide says. What I'm trying to say is if your step size is small, then the discretization will closely follow the continuous time process. Therefore, it will inherit all these exit time properties as well. Okay, so more interesting part. So right now, let's assume that this alpha stable driven stochastic differential equation is a good model for SGD. So under this assumption, so right now we are not going to question the accuracy of this approximation. Now the question is going to become, if I assume that this is exactly my algorithm, so my stochastic optimization algorithm is exactly this stochastic process, can we deduce some like information about the generalization error, and can we formalize this like theoretically? So first of all, by generalization, what do I mean? So essentially, like informally, I mean the difference between the training error and the test error. So I'm interested in coming up with upper bounds for this quantity, because if I can upper bound this difference, then I can try to estimate my test error because like I can compute my training error, obviously, because I have a training set. And if I sum up my training error and this generalization gap, this would give me an estimate for the test error as well. And then I could estimate the test error without having access to any test data, right? So this is the interest in trying to upper bound this generalization gap. So there have been tons of different generalization bounds for neural networks. So it's a really, really active field of study. And one big problem with current bounds is that these bounds often grow with the number of parameters in the model. So for instance, this is taken from a paper by Behnam Neyshabur, and it shows the following. So here, this is a real neural network, like a small one, and I think it's a single hidden layer neural network. And what they look at is they increase the number of parameters, and then they monitor the behavior of the training and the test errors. And the classical learning theory essentially says us that if you increase your number of parameters beyond a certain point, your test error should degrade. I mean, your test accuracy should degrade. And these bounds are essentially meaning that, and then these bounds are essentially saying that as you increase the number of parameters d, then the bounds grow. Essentially, they indicate that the error is going to grow as well. But then if you compute the real error on real problems, this is not the case at all. So as you increase the number of parameters in your network, then the performance is essentially getting better and better. So this is totally conflicting existing learning theory. And now, okay, I mean, why am I talking about this? As I said, I'm going to assume that this alpha stable driven stochastic differential equation is going to be a good model for SGD. So I'm assuming this, and I'm going to try to develop generalization bounds for this process. And as a byproduct, we will also address this problem that I just described, the problem of like exploding upper bounds with respect to the ambient dimension D. So, I mean, the idea was already there empirically. So I want to mention like two other papers related to this, especially the paper from Martin and Mahoney from 2019, where these authors observed a heavy-tailed behavior in the covariance matrix, I mean, the inner product of the weight matrices. So if W is your weight matrix for a given layer, and if you compute W transpose W and look at the distribution of the singular values, they observed a heavy tail structure on the singular values. And then they realized that the heaviness of these tails correlate really well with the test accuracy. So here, like this is the tail index that they compute over these empirical spectral distributions. And then they see that there is a super, like very nice linear trend. And then you can try to use this tail index as a complexity measure for your neural network. So if this alpha is small, then your network is less complex, therefore you will have better generalization. So this was, but this is totally empirical. And then here we will try to make all these arguments more rigorous. So before going to the theoretical contribution, I just want to give some preliminaries. And I'm not going to define anything mathematically, but just pictorially. So let's talk about I just want to talk just a little bit about fractal geometry and the quantity called the Hausdorff dimension. So here we see this Sierpinski triangle. I think, I don't know how to say this in Polish. Sierpinski, I guess. So this Sierpinski triangle is this. So it's a self-similar object. So if you look at this top part, it is essentially the same as the whole. So this whole just repeats itself like 3 times here, and then it's just a recursive object. One interesting question is like, what is the dimension of this object? So it looks like a 2-dimensional object because like it's on the plane. But if you compute the area of this object, it is equal to 0. So then it is a bit absurd. You cannot really have a 2-dimensional object with 0 area. So then it must be 1-dimensional. But then it is really not 1-dimensional. If you try to compute its length, like the 1-dimensional Lebesgue measure, it is infinite. So it's an infinite length, 0 area object. So it is something a bit weird. Then fractal geometers came up with different notions of dimension, and Hausdorff dimension is one of them, which essentially generalizes the usual notion of dimension to fractional values. So now the dimension does not have to be an integer, so it can take any positive number. And here, for instance, for this object, if you compute this quantity called the Hausdorff dimension, it is essentially a number between 1 and 2. So it's more than 1-dimensional, less than 2-dimensional. And then this Hausdorff dimension is going to be the key for our generalization bounds. So one observation now, I think this is the key observation. It turns out that Markov processes generate fractals. So since Markov processes are recursive processes, fractals are often generated by recursions, and then it's not a big surprise that if you look at the trajectories of Markov processes, they have some fractal structure. And more interestingly, if you look at the Hausdorff dimension of these fractals generated by Markov processes, it turns out that the Hausdorff dimension is directly related to the tail behavior of this Markov process. So let me try to illustrate it with this very simple example. Here I'm showing 3 different 2-dimensional processes. So the first one is, they are all alpha stable processes with different alpha in 2D. The first one is alpha equals 2, which is just Brownian motion in 2D. This one is alpha equals 1.5, it is heavy-tailed. And this one is alpha equals 1, it is more heavy-tailed than the first one. It is also called the Cauchy process in 2D. If you look at, so now these are processes in 2D, so we need 3 dimensions to visualize it. And if I just look at, so okay, let's take this process, and if I just look at all, just the trajectory, so if I just discard the temporal information and I just put all the points that my process visits in a single set, which I call the image of the process, then we obtain these 3 different pictures. So this is the the trajectory put in a same set, coming from this Brownian motion, and similarly for these other processes. So here the interesting thing is, even though the number of points are exactly the same in each of these sets, we can definitely see the complexity, in some sense, of these sets are totally different. So even though we have the same number of points in this picture and this picture, we can see that in the Cauchy version, the allocation of the space is much less. And it turns out that if you compute the Hausdorff dimension of these sets, of these image of these processes, the dimension is exactly equal to alpha. So for this process, the dimension of this set is equal to 2, the dimension of this set is equal to 1.5, and the dimension of this set is equal to 1. So this essentially says that the heavy tails does not only change the statistical structure of the process, it also determines the geometry of the process as well. And then as the process gets heavier tailed, the geometrical structure of the process gets somewhat simpler because its dimension gets smaller and smaller, and the smaller dimension essentially indicates less complexity. Okay, so now this will be the main idea in our generalization model. So let's proceed with the generalization model. Now I'm going to define the mathematical setup, which is essentially just the classical supervised learning theory setup. Here we are assuming we have a data space Z, which is a product of features and labels. We assume that we observe a training set of n IID elements coming from an unknown distribution, unknown data distribution. And we assume that we have a training algorithm which has two inputs. So it takes the data set as an input, and it also takes a random variable which encapsulates all the randomness happening in the algorithm. So if it's a stochastic optimization algorithm, the stochasticity of the algorithm is going to come from this random variable, and S is going to denote just the data set, which we assume to be a random sample coming from the product measure of this unknown data distribution. And we are going to assume that this training algorithm does not only give us a single output, but it gives us the whole trajectory from a continuous time 0 to 1. So normally we would train our neural network and we would just keep the last element. But right now I'm going to assume I'm going to use the whole trajectory. And since I'm in the continuous time assumption because of this processes, I'm going to assume that I observe this trajectory from time t0 to t1. So it's a continuous, it's a trajectory with continuous time. And as a proxy for SGD, as I mentioned, I'm going to propose, and I'm proposing this SDE as the algorithm. So here, it's essentially the same thing as I described in the previous part, but this time I need to be more careful with the data set because of this, because we are in the generalization bound setup. So the SDE contains three parts. The first part is the gradient flow, essentially. So we have a loss function which depends on the data set, which makes sense. And we have two different sources of noise. We assume there is some sort, there can be some Gaussian noise. It doesn't have to be present, so we can just choose the sigma 1 matrix to be 0. So we just use this to be more general. And then we also have a heavy-tailed noise, which is coming from this alpha stable process. And everything is state dependent in this setup. And we are going to choose, even though I'm not going to write it explicitly in our heads, the algorithm, the training algorithm is essentially going to be, the trajectory of this training algorithm will be obtained by the trajectories of the stochastic process. This is the model for the training optimization process. Here I'm going to consider, to measure the quality of the estimates, I'm going to consider a loss function L, and I'm going to assume that it's uniformly bounded by a constant C, and it's Lipschitz in W with Lipschitz constant F. Then I define my population risk or the true risk. As the expected loss with respect to the data points. And the empirical risk is just the empirical average of the loss on the training data set S. And I will be interested in the difference between the true risk and the empirical risk, because the true risk will essentially indicate the test error because it contains all the information about the data distribution, and the empirical risk is just computed on the training set. So it is exactly the training loss that we are considering. All right, so now I can present the main result. So as the hypothesis class, it might look a bit complicated, but it's just simple. I'm denoting this WS as a parametric hypothesis class, and I'm just taking the trajectory of my algorithm from time t equals 0 to time t equals 1. So I'm essentially simulating my optimization algorithm from t0 to 1, and I'm just putting all the parameters seen on the trajectory into this set WS. So this is the image of the process that I mentioned in a couple of slides before. And the theorem is as follows. So under several assumptions, some of which are not really trivially satisfiable, under some assumptions with high probability, we have this bound. So the first of all, what we are looking at is the worst case generalization gap over the trajectory. So I'm looking at, okay, what would be the worst generalization error that I can happen to see on this trajectory given by this process. And we can see that it is essentially upper bounded by two terms. The first term is the Hausdorff dimension of this set times some terms which are not essential. And the second term contains a constant which essentially measures the statistical dependence between the training loss and the geometry of the trajectory. So it might sound a bit complicated, but you can just think about it as the mutual information between the training set and the Hausdorff dimension of the set WS. So we want to have some sort of decoupling between my training set and the geometry that my algorithm provides in our proofs, and then this constant m essentially measures that. So if my algorithm is essentially outputting trajectories which have similar geometric properties in terms of the fractal dimension, then this m is going to be small. But if these two quantities are like very dependent to each other in terms of statistical sense, then this m might be very large, even infinite. All right, so this is the bound that we provide. And first of all, the first observation is that we can immediately see that the bound improves upon other bounds which have a d here instead of this Hausdorff dimension ws, because by definition, the Hausdorff dimension is less than or equal to the ambient dimension. And if this number is way smaller than d, then our bound directly improves upon existing upper bounds. And secondly, and more interestingly, this is coming from a different paper from 1998. And so, I mean, it would be impossible to write it down rigorously because it has a very involved notation. But essentially, it says that if we consider the stochastic differential equation, which I showed in the previous slide, the Hausdorff dimension of its trajectories is upper bounded by the tail index around the local minimum. So when your algorithm goes near a local minimum and starts emitting some diffusive behavior, so it starts making some sort of like a random walk, then the tail behavior of this random walk is essentially going to be like the tail index for this random walk is going to upper bound the Hausdorff dimension of the whole trajectory. So this is a very interesting result. And then if we combine this theorem with the theorem we proved, it essentially says that the generalization error is going to depend on the tail index around the local minimum that the algorithm finds. So this is the intuitive explanation. I mean, or this is the rigorous explanation of the empirical behavior that we observed in the past. And we have other results in the paper too, but just before concluding, I want to show a couple of empirical results. Because, I mean, the nice thing about this is we can try to compute the tail index. We don't need to compute the Hausdorff dimension by using geometrical tools. We can try to compute the tail index, which we know that is going to be an upper bound for the Hausdorff dimension. So this is what we observed. So here each point is the tail index. I mean, so we monitor the generalization gap versus the upper bound on the tail index that we can compute. And here each point represents a different neural network. So each color is a different size. So here we consider VGG nets, which contains both convolutional and linear, like fully connected layers. And each color represents a different size. And then for each color, we have like different instances, which indicate we change the hyperparameter. So there are different step sizes and batch sizes for each given model size. And we can observe that there is a clear linear trend with respect to the upper bound that we find and the generalization gap. And again, like more interestingly to me at least, even when the number of parameters is very large, for instance, for this, I don't know, like this Bordeaux case, when we have like 19 layers, like D is the depth, we have 19 layers network. The total number of parameters is around like 20 million. But if we compute the Hausdorff dimension, it can be much smaller than, I mean, it's like way smaller than 20 million, essentially. And then it shows that the number of dimension, I mean, even if we increase the number of dimensions, the intrinsic dimension of these neural networks do not need to increase as well. So this is this is a surprising outcome, in my opinion. And to compare this with the existing, some of the existing bounds in the literature, So one popular option is the norm-based metrics, but I'm not going to plot them because we know that they are increasing with the number of dimensions anyway, so they are not going to be able to capture this structure. And two other like complexity notions are one of them was I mentioned in the beginning, like this tail index for the empirical spectral distribution, and the other one is the ratio of the step size to the batch size. And here we can see some sort of correlation between these measures and the generalization gap, but we can also see that they cannot really capture the full picture, so they are only accurate in some ranges. So this concludes the second part. So I'm going to skip the third part. So let's just jump over the conclusions, and I can take questions about the third part, which which essentially explains why these heavy tails are happening. Okay, to conclude, the take-home messages are as follows. So first of all, we observe that SGD can exhibit non-Gaussian heavy tail behavior. And I didn't talk about it, but this heavy tail behavior is essentially a function of the step size and the batch size. So this is the originating cause of the heavy tails. And I claim that this alpha stable noise assumption seems more appropriate, arguably more appropriate, at least compared to the Gaussian case. And we have seen that there's a strong interaction between the geometry and the dynamics. So if we change the dynamics by changing the hyperparameters, it also changes the geometry of the process as well. So this is quite interesting. The existing metastability theory for these processes already shed more light on the wide minima phenomenon if we assume that we have this simplistic one-dimensional setup. And we have linked the generalization error to the heavy tails through the Hausdorff dimension of the trajectories. All right, so this concludes my presentation, and thank you very much for your attention. I'm happy to take questions.
Thank you so much, Umut. Let's thank our speakers. Maybe you can unmute and we can clap.
Thank you.
Questions?
So I see some questions.
I can start with one. Then we should be able to train a neural network with this SDE, like meaning that like we do actually gradient descent, but we generate this heavy tail noise, and that will be your training instead of SGD. Have you tried that? And that will give you control over full control over the noise distribution, right?
Yeah, I mean, this is, you are totally right. So at some point we tried this. So here, okay, let's consider this SDE. So if we want to mimic the behavior of this SDE, then we need to estimate all these additional scalings as well. So only estimating the tail index is not sufficient to be able to simulate the whole process. And we realized that trying to estimate all these things is very difficult. And each time we tried, we couldn't really, I mean, because of the estimations, the processes diverged each time. So we failed to do it. So it is still open. And if you are interested, I'm definitely open for like looking at this question. So the answer is, it is totally right, but we couldn't really replicate this behavior.
Thank you. Any more questions? Okay. Yeah, so maybe another question from me. Sorry, I'm hogging the the questions, but so the complexity of the distribution of the data is another thing that's interesting. It kind of goes back to that batch size question, right?
Mm-hmm.
I can imagine if my input distribution, my data is just like Gaussians, right? It's like there is not much complexity,
Mm-hmm.
right? As opposed to if I have MNIST, as opposed to if I have CFAR, which is like more complex. Like the role of this complexity of the input distribution or the data, like where does that show up?
Yeah, like really great questions. So okay, let's go to the third part. So it will directly answer this question. So in this third part, we try to understand where these heavy tails are coming from. And then we considered a super simple problem. where, I mean, the problem is a linear regression with quadratic loss, and the data is coming from a Gaussian. Okay, so something similar to what you said. So let's assume this A is a random vector in RD such that it has zero mean and it's Gaussian with zero mean, and then small sigma squared times identity covariance. Okay, super simple. It turns out when you write the SGD recursion, but this is online SGD. So at each iteration, you draw a new data sample. You don't reuse them. You can rearrange some terms, and it can be written like a matrix times your previous iterate plus a random vector. So some random matrix times the previous iterate plus some random vector. And what we showed, and in fact we relied on a lot of results from financial mathematics. So just don't read this part. Let's just look at here. So here I'm assuming the SGD recursion has a stationary distribution. So it's a Markov chain and it has a stationary distribution. And the tail index of the stationary distribution is equal to alpha. And alpha is the number. So if you look at this HS, alpha is the number which makes this expectation equals to 1. So you are looking for S such that this expectation is equal to 1. And then this is going to be the tail index of your stationary distribution. So then what does this alpha depend on? So it depends on the Hessian of your loss. It depends on the step size and it depends on the batch size. So even with this simple Gaussian setup and linear regression with quadratic loss, if you have large enough step size, if you have small enough batch size, or if you have large enough covariance, large enough variance for your data, you can still have heavy tails in the stationarity. So this essentially shows it is not really fantastic, like, or like very, I mean, you can achieve heavy tails even in this simple setup. And the model that we use for this heavy tail stochastic process is essentially mimicking the behavior at stationarity. So this model is not really good for earlier parts of the optimization process, but it is good for the case where optimization algorithms already exhibiting some heavy tails.
Fantastic. Thank you so much, Umut. I know a lot of people have already left because the classes are starting at 1:15.
Yeah, no
Let's
problem.
thank our speaker once again. Thank you.
Thank you.
Stop recording now.